Welcome to the next video in the course in real analysis. This is lesson 5 on ordered fields, and this is the solution video to the exercises presented in the previous video. So let's recall the first exercise, which was to show that if we give the complex numbers the dictionary ordering, then it is not an ordered field. And so here we have the definition of the dictionary ordering. And to find why it is not an ordered field, well, we're going to have to find some axiom that is violated. Now, we already know, because we discussed it in a previous video, that C with its plus and times operation is a field. So we shouldn't go looking in those axioms to find a contradiction. We know that the dictionary ordering is a total order from a previous video. So again, we shouldn't look for a contradiction there with the axioms. And so I will just go ahead and note without proof that in fact, if we include, right, if we put them together with the plus and times and less than relation, the result is compatible with addition, right? That this less than or equal to relation is compatible with addition. So I just promise you that, and you're free to prove it if you like, but I'm just going to claim it here without proof. And all of this is to say that we should therefore focus our attention on showing that less than or equal to is not compatible with multiplication. That's the one that's going to fail here. And so let's just jot down in the margin here that what I'm saying is that I can find a choice of A less than or equal to B, and I can find a choice of C strictly greater than 0, such that AC is not less than or equal to BC, so not less than or equal to BC. I claim that I can find complex numbers A, B, and C, which are like this, basically. So what are my choices of A, B, and C? Well, I'm going to choose A to be 1, so that's my A. I'm going to choose B to be 1 plus I. And note that A and B have the same real component, 1. A has imaginary component 0, and B has imaginary component 1. Therefore, by the dictionary ordering, since they are tied in the real component, but B has a bigger imaginary component, then B is bigger. Okay, so there's my A and B, and next let's choose C. I'm going to choose C to be the number I. And this is strictly bigger than 0 because, after all, 0 has real and imaginary components both equal to 0. I has real component equal to 0, so it's a tie, but then has imaginary component equal to 1, and so since 1 is bigger than 0, then I is bigger than 0. Which is what we need for these conditions. And so I have my choice of A, B, and C, right? So A is, in fact, less than or equal to B. C is, in fact, greater than 0. Now let's consider what happens when we multiply A by C. Well, the multiplication of A by C is 1 times I, which is I. Then we also have to multiply B times C. So B times C is going to get us I minus 1, keeping in mind that, of course, 1 times I is I, but then I times I, that's I squared, which simplifies to negative 1. Okay. Now, the question is this inequality true by the dictionary ordering? Well, let's, rearrange the I minus 1 into negative 1 plus I, just so that we see that the real component comes first. And here it is negative 1. And that's all we really have to talk about, because when we look over at the other thing, which is I, its real component is 0, making it bigger than negative 1. And so, in fact, this is the ordering according to the dictionary ordering, which is not what we need for, and in fact, I guess I should put less than or equal to, but in any case, this is, not what we need for compatibility with multiplication. Therefore, compatibility with multiplication fails. Therefore, the complex numbers with the dictionary ordering is not an ordered field. Proof complete. Okay, moving on to the next exercise, let's recall what it was. We will show that in any ordered field, strict less than, or strict precedence, is compatible with plus and times. And here I have to tell you what that means, or I guess I shouldn't over-explain this because I've already explained it once before, but this is what compatibility means. And so we will prove that strict less than is compatible with these. So for the proof, we will pick A, B, and C in our field, and in particular, we will assume that A precedes B. Now we need to show that for whatever the choice of C, that A plus C precedes strictly B plus C. How are we going to do it? Well, almost certainly this has to go through the compatibility with addition that is true for pre-seek. So since immediately by definition, A precedes B tells us that A pre-seeks B, then we have A precedes B, and by compatibility with addition, we can add, and there's a typo here, sorry, this should just be B plus C. So it's taking this and using compatibility with addition, which allows me to add C to both sides. And then, well, we have, sort of most of what we need for strict precedence. The only problem is that it's not strict. And so we need to rule out the possibility that A plus C equals B plus C. So in order to rule out that possibility, we will show that it is not true, and we will do so through an argument by contradiction. So for contradiction, we will assume that they are equal. We can subtract C from both sides, get A is equal to B. But we know that A precedes B, and that directly, by definition, entails that A does not equal B. So we get a contradiction, and then we are now able to say that because they do not equal each other, right? So since A plus C does not equal B plus C, and again, I have this same typo, so that should instead be that A plus C precedes strictly B plus C. So there is the proof for compatibility with addition. Now let's prove compatibility with multiplication. So with A and B as before, but this time we will further assume that C is strictly positive. Well, we know immediately, and I'm doing several steps very quickly all at once, but we already know that A precedes B, because we're still assuming that A precedes B. So we get A precedes B immediately. We also have that 0 precedes C, and then by compatibility with multiplication for pre-seek, we get that AC pre-seeks BC. So that's where this part comes from. Again, at this point, we only need to rule out equality. So for contradiction, let's assume equality of AC and BC. Now, this is where it's important that we said that 0 strictly precedes C. That tells us that C must not equal 0. Because C must not equal 0, then therefore by the field axioms, any non-zero element has a multiplicative inverse. This tells us that we are free to take this equation and divide throughout by C. So if we divide throughout by C, then AC over C simplifies to just A. BC over C simplifies to just B. And so we have that A is equal to B. Again, right, that's an immediate contradiction because we knew from before that A precedes B, and therefore A does not equal B. So we've got that A equals B, but we also have that A does not equal B. There's our contradiction. This is what tells us that this equality must be false, and that all tells us that therefore AC strictly precedes BC, which is exactly what we needed to show in order to show that strict precedence is compatible with multiplication. Okay, moving on to exercise number 3. Let's consider any arbitrary ordered field. We will define the symbol 2 to refer to 1 plus 1. And by the way, I guess it should be obvious, but I'll go ahead and say it, that this must be an element of the field because a field is a group under addition. And when you talk about a group under addition, you have the closure property. This is the fact that the plus operation is an operation. So whenever you take any two things and add them together, you get another thing in your field. Anyway, I think that was probably already clear, but maybe worth saying. Okay, we are going to show that 1 strictly precedes 2. That's going to be our starting place. Then we'll come back around to the rest of this. Now, the proof is nice and short and sweet. We already know from a previous video that 0 precedes 1, strictly. From compatibility with addition for strict precedence, right? I mean, and to some degree, this is why I wanted to prove compatibility with addition for strict precedence, is so that I could make this move right here, and we've already justified it. Of course, it was also a good exercise to go through that, but also it is useful so that I can use it here. In any case, we now have that 1 strictly precedes 2. Now, I'm going to skip a little bit, but I'm going to leave it to the viewer to show that if any number, any x in your field is positive, then it follows that the reciprocal is also positive. But I'm going to assume this. I recommend proving it by contradiction, but I leave that to you. In particular, we will apply this where x is equal to 2. So since we know that 2 is strictly bigger than 0 by transitivity, then we know that its reciprocal is also strictly positive, and so that gets us yet another part of what we are to show in this exercise. Finally, what I can do is I can now take these two things, right? The fact that 2 is strictly positive, treat it kind of like C in the compatibility with multiplication, and treat each of these, for this portion, I would treat 0 like A, and I would treat 1 like B. For this portion, I would treat 1 like A and 2 like B. But in any case, by basically just a series of applications of compatibility with multiplication, I can multiply throughout the entire chain of precedence by 1/2. And when I simplify everything, I get this. And that is effectively the end of the proof, because we, basically through transitivity, we can finally state the full statement, which is that 0 precedes 1/2 precedes 1 precedes 2. But that's it. That's the end of that part of the proof. Next, we're going to talk about the average. So if you take any two numbers, A and B, and we say that their average is A plus B divided by 2, which note, I'm not sure if I've already commented on that, but this is the same thing as multiplying 1/2 by A plus B. That might be just obvious already, but if you want to see it in terms of our field operations, where our only field operations are plus and times, then that's how you understand this as being constructed only out of the official field operations. But anyway, we're also going to assume that A strictly precedes B, and then we're going to show that the average is in between. And in particular, to get started, we're going to show that A precedes A plus, or the average, right? I am going to prove that. I'm also going to leave the proof of the other side to you, it should be almost exactly identical to what I prove here. And so for that reason, I'm gonna, it's a good exercise for you to kind of repeat what I do, but just with a few things changed around. But anyway, to prove this direction, right, to prove this part where I'm going to show you that A strictly precedes the average, well, this inequality is exactly equivalent, right? You can easily prove that it holds if and only if you multiply the 2 to the other side effectively, which is valid because we know that 2 is strictly positive. Then from here, we can subtract A from each side, which is always a valid move to make by compatibility with addition. And then simplifying that, you get that, and I'm going to leave it to you also to show that 2A minus A is equal to A. Showing this should be quite easy. Think about distribution and factoring, but I'll leave it at that. But in any case, we do get that A strictly precedes B. Now, because we assumed, right, this A precedes B was an assumption of the problem, then since this is true, therefore this is true, therefore this is true. And so that is the proof that A strictly precedes the average. Okay, moving on to the fourth exercise. Again, we have an ordered field. This time we'll have a non-empty subset of the field, and we will show, to begin with, that if this non-empty subset Y has a supremum, then that supremum has the following two properties. Later on, we will show that in fact it goes the other way around, and this altogether I call the alternate characterization of the supremum. So maybe I'll go ahead and make a note of that here. The alternate characterization so the alternate characterization of suprema, of course, there's also a corresponding alternate characterization of infima, but in any case, that's what I'm going to call it because, right? Because if it is if it is the supremum, then it has these two properties. If some number has these two properties, then it is the supremum. So since it kind of goes in both directions, this is an equivalence, and so. Right, you could kind of, what that tells you is that you could think of the supremum in the way that I have already given, or you could think of it this way. I guess notice that is only in the context of an ordered field, but in any case, so important result, and we'll start proving it. Now, suppose that alpha is the supremum of Y. Now, by definition, that just means that it is the minimum of the set of upper bounds of Y. After all, that is simply how we defined the supremum. How we defined the minimum tells us, for one thing, among other things, but it tells us that alpha is an upper bound of Y. So, in fact, the showing that the supremum has this first property of being an upper bound of the set Y is really immediate. But the other property takes just a little bit more work. We need to let epsilon be any positive field number. And we need to show that if you take alpha minus epsilon, that is not an upper bound of the set Y. So, well, certainly you get very quickly that alpha minus epsilon is smaller than alpha. And that's very easy to prove. You can simply take this, subtract epsilon on both sides, then you can add alpha and you get this result. So very easy to demonstrate that. Now, we also showed in a previous exercise that if you have a minimum, which after all we do, alpha is the minimum of this set. And we showed that if you have the minimum for any set and you take a smaller number, which we now have a smaller number, then that thing cannot be in the set. So effectively, since alpha was the minimum of UBY, and this thing is smaller than alpha, then this thing cannot be in UBY. That is precisely the result that we wanted to obtain. So therefore, the supremum has the two stated properties. And next we'll work on the reverse direction. So suppose that alpha is some number in the field which has the two properties, which is to say, it is an upper bound on the set Y, and also for any positive real number, alpha minus epsilon is not an upper bound of the set Y. We need to now show that alpha is the supremum of Y, which is to say it is a minimum on the set UBY. Again, part of this is completely trivial because, again, the definition of minimum is that it be in the set and also a lower bound of the set. That's just the definition of the minimum of any set. Well, being in the set is given for free by that first property. So then all we have to do is show the second property, which is the second property of being a supremum, right? What is the second property of being a supremum? It is, or sorry, and then of being the minimum, right? So we already have the first property of being a minimum. Now we need the second property of being a minimum, which is to be a lower bound, right? That's part of what it means to be a minimum as well. So we need to show that alpha is a lower bound on the set UBY, which is the set of upper bounds, right? So it's a lower bound on the set of upper bounds. And by the way, you might not have quite realized that that's what we mean when we talk about a supremum, is that that it is the least upper bound, right? So this is another way to say what, or sorry, this is another way to say what a supremum is that it is the least upper bound on the set Y. But anyway, so that's now what we need to show. We need to show that alpha is a lower bound on the set of upper bounds of Y. Well, to show that it is a lower bound on, well, any set, we want to take something out of that set and show that our chosen object, in this case alpha, precedes that element of the set. So this is what we need to do. We need to pick an arbitrary element out of the set of upper bounds and show that alpha precedes it. Okay, we will actually show the contrapositive, the other way around, right? If beta is strictly precedes alpha, because that is, after all, the negation of alpha precede beta, the negation of that is beta precedes alpha. We showed that in another video. So for the contrapositive, we will assume that and prove the negation of this, which is to say that beta is not an upper bound of Y. Why am I choosing to show the contrapositive instead of go directly for the statement? Well, if you think about it, you know, let's draw a picture to somewhat motivate this. And just imagine that your set Y, I mean, who knows what your set Y? It could be some crazy chaotic set of real numbers on the number line. So maybe just as a very abstract painting of the set Y, perhaps it looks like that. But we know that it has an upper bound, that alpha is an upper bound. And moreover, we can't draw alpha out here, because if we did, then you could say, well, you could go a little bit lower than alpha and still have an upper bound, but we know that that's not true, right? That if you go any lower for alpha, that you don't have an upper bound. That's kind of the whole idea of property number 2. So you have to somewhat draw alpha right up against the set Y and say if you went any lower than that, then you would have not an upper bound. That is essentially the idea of alpha. And so proving this contrapositive puts beta below alpha, and that makes it, in fact, actually just very trivial that beta is not an upper bound, which is exactly our goal. So that's why approaching the contrapositive is easier than approaching the original conditional, is just the property as we had stated it. Property number 2 is, just interacts much more naturally and nicely with this beta strictly precedes alpha. So that's why we're going for the contrapositive. Okay. Now, as a somewhat useful thing in its own right, it is not that deep, but it can be useful. I'm going to show a lemma which sort of establishes that that beta is less than alpha if and only if there exists a positive epsilon, of a certain sort, I guess I could say. Like, basically this is going to kind of quantify, whenever C is less than D. Let's start talking in the language of this lemma. Whenever C is less than D, then there exists a positive number such that C plus that positive number is equal to D. In a way, what this kind of does is says, yes, C precedes D, but we can even introduce this precise quantification of how much it precedes D. So, right, so again, thinking about the number line, putting C over here, D over here, then this gap between them, epsilon, right? C plus epsilon equals D. So epsilon represents the distance between them, or, in another way of putting it, by just how much does C precede D. And these go vice versa, right? So if C precedes D, then this epsilon exists, and if epsilon exists, then C precedes D. It's a natural intuition when thinking geometrically about the number line, but of course we can't just think intuitively. In real analysis, we are trying to give rigorous proofs. So this is what we will prove, and then it should make demonstrating this right here very, very immediate. So, okay, proof of the lemma. Let's assume that C strictly precedes D, and I claim that if we set epsilon equal to D minus C, then we will get exactly this result, that there exists a positive epsilon such that C plus epsilon is equal to D. Okay, it is totally clear that epsilon, so chosen, is strictly positive. How do we know? Well, let's just take this and subtract C to the other side. So we know that 0 strictly precedes D minus C, but then D minus C is precisely how we defined epsilon. So there you have it. By the way, I feel like this might be a good moment to note something about how to approach mathematical proofs generally. A lot of times we present these concepts in sort of like abstract ways with just like this list of axioms, and it just feels like a set of rules. But then when you are given the task of proving some theorem, you want so like in this particular problem, right, where we're going from C precedes D to the task of showing the existence of a positive epsilon, blah, blah, blah. How do you pick that epsilon, right? That kind of question is common when you are, struggling with proofs. And, even when you see the demonstrated choice of epsilons, or in other cases, something more complicated, you might say, well, okay, I can, follow the proof. But how did you ever come up with that number in the first place? And so what I want to emphasize is that it's the geometry, right? Like thinking intuitively is still, right, even at this advanced level of mathematics, even when we're dealing with very abstract ideas and proofs, you want as much as possible to try to intuit these things, especially with nice pictures, so that they give you the motivations for the formal rules. So, I just want to kind of emphasize that as advanced and formal as all of this is, you want to make the connection between your intuitions and the formality, and you want to develop the skill of adeptly moving back and forth between the intuitions and the formality. And this is a nice exercise in doing kind of exactly that, using the geometry of the number line to tell me what I ought to expect my epsilon to be. But okay, so having given that philosophical note, let's continue. So we know right? We have so far explained why epsilon is positive. And also, if you do C plus epsilon, if you just crunch through the calculations, which is not bad at all, C plus epsilon is the same thing as C plus D minus C. Put the C's together, they cancel, and you get D exactly as promised. And there it is. That is the demonstration of the left to right direction for this lemma. Okay, how about the converse? Well, we're going to assume the existence of this positive epsilon, so on, so on. And now we want to demonstrate that C is less than D, or C precedes D. Well, okay, how are we going to do it? We need to use this fact that epsilon is bigger than 0. And so let's solve for epsilon, right? And so if we solve for epsilon, then we get that epsilon is equal to D minus C. And we know that epsilon is, that 0 precedes epsilon. Epsilon is D minus C. So we have that 0 precedes, right, by transitivity, 0 precedes D minus C. Now add the C back to the other side and you get the desired result, and the proof is complete. Okay, applying what we just showed to what we were going for this whole time, we are trying to show that if beta precedes alpha, then beta is not an upper bound of the set Y, like we said a couple slides ago, right? And keeping in mind, remember, what are these things? Y is a non-empty set. Alpha is an element with the property that it is an upper bound, and alpha minus epsilon is not an upper bound for any positive epsilon. Okay, well, from the fact that beta is strictly less than alpha, we now know from our lemma that there exists a positive epsilon such that beta plus epsilon is alpha. More apropos for our current purposes is to get that alpha minus epsilon together. We now know that beta is alpha minus epsilon. From the property that we assume alpha to have, this immediately entails that beta is not an upper bound of Y, and that basically concludes the demonstration that alpha is the supremum, right? Let's connect this all the way back to why we were doing this in the first place. Is we needed to show, right? Needed to show that that alpha was a lower bound on the set of all upper bounds of Y. To do that, we wanted to show that if you pick any beta out of the set of upper bounds, then alpha is less than or equal to beta, right? Because that's just the idea of a lower bound, right? This here is the idea of a lower bound. We took the contrapositive of that, which is to show that if beta strictly precedes alpha, then beta is not an upper bound of Y. And this is what we have now finally shown. So we have exactly what we set out to prove. Since we already had the other property of being a minimum, we now know that alpha is the min of the upper bounds of Y, which is to say alpha is the sup of Y, and the proof is complete. So there we go. And I'd like to close out the video with an invitation to ask questions. If you found anything confusing in this video or in related parts of the textbook, feel free to leave a question as specific as you can in the comments. And if I can address it in the comments, I will, or otherwise I will make a video to address it and insert it into the playlist.